All right, welcome back. This is the Research Computing Facilitators Virtual Residency 2025. I'm Henry Neiman, and we're in our second talk on Monday, June 23rd, 2025, Effective Communication. So let's dive right in. Here's a quick outline. We're going to talk about how to talk to researchers, and in particular, research terminology. We'll compare enterprise IT with research computing to understand the differences between them and the key difference between them. We'll talk about the mindset gap. We'll talk about types of researchers, what to say to a researcher, how to find researchers, and how to find their research projects. So let's start with terminology. So by show of chat, so to speak, how many of you believe that oxygen is a metal? So if you believe oxygen is a metal, go ahead and in the chat say me. And I want to note for the record that so far, not a single person here has put anything in the chat about believing that oxygen is a metal. Somebody says sometimes if you're an astronomer, somebody says me, somebody says it depends. That's 3 answers out of 118 attendees. Here's a fourth. So 4 out of 118 believe that oxygen is a metal. All right, so what is oxygen? Well, it's atomic number 8. Oh, there's a fifth. It's atomic number 8. It's a chalcogen. I don't know what the heck that means. It's a key element in life, in fire, in rust. You can't have water without oxygen, right? And so on and so forth. But what is oxygen in astronomy? Well, the universe is made of a bunch of ingredients, but almost all of the universe is hydrogen and helium. And here, by the way, I mean visible matter. I'm not talking about dark matter. Nobody really knows what that is. But all of the visible matter of the universe, hydrogen is hydrogen and helium, and an itty bitty tiny bit, a little bit of flavoring, a little bit of spice of things that are not hydrogen and helium. So hydrogen, atomic number 1, that's 75% of all baryonic mass. I don't know what the word baryonic means in this context. Most stars are made of hydrogen and so on. Helium is atomic number 2. It's an inert, it's a noble gas. It's 24% of total elemental mass. I do not understand the distinction between baryonic mass and elemental mass, but I'll leave that to the physicists. And everything else combined, including oxygen, but everything else combined is 1% of the visible matter of the universe. Everything else combined, 1%. Okay. Now, what are planets made of? Planets are made of metals in the chemical sense, right? So the cores of planets are typically iron and nickel. So, for example, Earth is 89% iron, 6% nickel, 5% everything else combined. Typically, the mantles are silicates, but the core, the bulk of the mass of a planet, is metal, right? So what is a metal? Well, if you're a chemist, the word metal has a very specific definition, right? And so here's a diagram I found on the web where you've got the green stuff is non-metals, the orange stuff is semi-metals, whatever that means, and the yellow stuff is metals. So most chemical elements are indeed metals. Not most of the mass of the universe, but most chemical elements are metals. It turns out that oxygen is not a metal in the chemical sense. But to an astronomer, and especially to a cosmologist, my PhD I did under a cosmologist, even though I'm a computer scientist. Metals to a cosmologist mean anything that's not hydrogen or helium. So if you talk to a cosmologist, and by the way, so I went to the weekly group meeting every week for years and years in my advisors group. And for the first, I don't know, 3 years, I thought when they said metals, they meant metals, shiny, hard things. They meant not hydrogen nor helium. And that was a huge revelation when I figured that out. I was like, oh, But why would you use the word that way? Well, there's a couple of reasons. One is the word metals effectively means everything that's not hydrogen or helium. It means round off air. But also apparently at the sort of temperatures and pressures and so on that stars operate at, non-metals do start to behave like metals. All right. Projection. So here's another word that means different things to different people. So if you put a mathematician and a psychologist and a movie producer in a room together and you say, discuss projection, right? What kind of conversation are they going to have? Because to a mathematician, projection means to take something in a higher dimensional space and put it into a lower dimensional space. So for example, I have a 3D cube, but when I draw a picture of it on paper, I draw two cubes and then some diagonal lines between some of the corners, right? If I take a four-dimensional object, a four-dimensional hypercube, and project it down to 2D, it's two cubes, a small one inside a big one, and then there are lines connecting the corners of the small one to the associated corners of the big one, right? That's projection in math. What's projection to a psychologist? That's where you assume that other people are experiencing or feeling the same thing that you are. And so you take what you are experiencing and you apply it to them. That's projection. What about to a movie producer? To a movie producer, projection means casting light through a colorful, or perhaps black and white, but transparent medium to produce a 2D image on a screen or a wall, right? So they're going to talk past each other. They're not going to come to a consensus about just about anything because they're going to be using that word projection to mean completely different things, right? So if you go to this YouTube link, you can watch the famous Who's on First routine from Abbott and Costello from back in the 30s or 40s or whatever, where the joke is that the names of the people they're talking about are also common words. All right, here's another one. What's a fluid? Well, we know what we think as sort of normal human beings. We know what the colloquial definition of fluid is. It means the same thing as liquid in colloquial English. And then, there's what your mom and your doctor think, which is what you should drink plenty of when you're sick, right? But what about in physical science and engineering? Well, in physical science and engineering, the word fluid doesn't mean liquid. It means not solid. So it means liquid or gas, right? And computational fluid dynamics, the most popular fluid studied in computational fluid dynamics is not a liquid. It's a gas. It's the Earth's atmosphere, air, right? So liquids then are incompressible fluids. They're fluids that if you push on them, they don't get smaller, right? And a comment, add another layer of unintentional hilarity when you add acronyms, and also different emphases. So depending on which syllable you put the accent on, you can get a different meaning. Okay, what is API? So when you have acronyms, right? To me, API means, gosh, what is it? The application programming interface. I use the acronym so often I forget what it stands for, but in medicine, it might mean active pharmaceutical ingredient, right? So in social science, fluid has another definition. So something that has room for interpretation, like gender, describing a feeling or a mood or someone's appearance. In finance, liquid means an asset that you can convert to cash, right? So who's right, by the way, about what the definition of fluid is? Well, the answer is very simple. They all are. Fluid means different things. The word fluid, and just about any jargon word, means different things to different people in different contexts. What's a database? Now, I was trained as a computer scientist. So to me, SQL and Oracle and Access and DB2 and MongoDB and things like that, those are all databases. And a large collection of files is not a database, but a bioscientist will use the word database to mean a large collection of files, even if they are not in the things that a computer scientist would consider to be a database. what's data and what's metadata? Metadata is data about data. So if you have a file of science data, that file probably also has a description of the kinds of science data that are in the file, and the particulars of the data that's in the file. So we would call that metadata. But if you are in the business of helping people search through large collections of files, perhaps petabytes and petabytes of files, then to you, metadata is the input into your algorithm for searching the data. So to you, the metadata is your data. And if you're a compiler developer, then to you, code is data, because you're going to take that code, the source code, let's say it's C or Fortran, and convert it into an executable, right? So is code data? Well, depends who you ask. Now let's talk about scale. So if you're studying a phenomenon that operates at quantum scale over femtoseconds, over tiny, what is a femtosecond? That's, I think, 10 to the minus 15th seconds, something like that, because I think it goes, or maybe it's 10 to the minus 12th. I think it goes like nano, pico, femto, or is it nano, femto, pico? I can never remember, right? If that's the length scale you're at, quantum scale, and that's the time scale you're at, an itty bitty tiny fraction of a second, how much does gravity even matter? But what about if you're operating at the scale of the entire universe over its entire lifetime, over billions of years? Then how much does gravity matter? It matters an enormous amount. It governs not literally everything, but it's got its fingers in every pie, right? At that scale. So what would be some examples of disciplines where gravity does matter and other disciplines where gravity doesn't matter? So in the Google Doc for this session, go ahead and put some examples and explain why gravity does or does not matter, right? By the way, this is a really good way to find out whether someone has a feel for disciplines beyond their own. If they can come up with an answer to that question, if they can straightforwardly name a discipline where gravity does matter and a discipline where gravity doesn't matter, or maybe we could say a research topic, okay, then they have some awareness outside of their own discipline. But I've met a ton of people who can't answer that question. But they can answer half the question, the half that pertains to their research area. What's the difference between science and engineering? Years and years ago, I had a grad student, and on his committee was a big science professor. And at his oral defense, after he stepped out of the room so we could discuss what he had presented, this faculty member said, well, I don't understand how what this engineering grad student did is research, because he didn't discover anything new about how the world works. And so I had to patiently explain that science focuses on discovery, understanding how the world works. Engineering focuses on design, how to leverage how the world works to create a capability, right? Like a building, a bridge, an electronic device, a new substance, new materials. Yes. So I thought I turned on the Google Docs for today and tomorrow already. Can you double check that? Okay, so science is focused on discovery, engineering is focused on design, but of course that raises some questions. Is a design project research? Do engineers do research? And if they do they do science research, or do they do engineering research? It may depend on the engineer. I've known engineers who do what I would consider discovery of physical principles, even though they're engineers. So there's more lines, to my mind, more lines with science research than engineering research, though I would never say that to them because I think they'd be insulted. Okay. So I thought I had already said it to public, but we'll do it after this one. Is research about software actually research, right? Do computer scientists even do research? I thought the purpose of computer scientists was to help real researchers actually do real research. And the computer scientists just wrote the code. By the way, my advice, never ever say that to a computer scientist. I was in the room once when someone said that. It didn't go over well. The same person also referred to the computer scientists as IT. That went over even less well. So don't refer to CS as IT, and don't poo-poo the idea that computer scientists do computer science research. They really, really do not appreciate that at all. Is simulated data actually data? So once upon a time, I had a colleague in chemical engineering who said that he could not go into a conference and refer to what was produced by a simulation that he had run as data. He had to refer to it as simulated data, and that if he referred to it as data, he would be laughed out of the conference. The issue of even words as simple as, like, to me, data means anything that you can express as ones and zeros. And it includes qualitative stuff. It's just how you express it as ones and zeros is a bit more elaborate, right? And again, remember, people who design compilers for a living, they consider code to be data, right? And they're not very interested in what everybody else thinks of as data. That's not useful to them, right? So what are some disciplines where they use the word data very differently from how other people use data, right? Yes, Lisp programmers, because your Lisp program can have as its input a Lisp program. Do researchers know what you know? The most common thing, the most normal thing in the world is to assume that other people know what you know. The second most normal thing in the world is to be dead wrong about that. Nobody knows what you know, or at least approximately nobody knows what you know. And you should never assume that they know what you know. And in fact, even on common knowledge stuff, they don't know what you know. So there was a study done that found that if you randomly select two people and you ask them what a penguin is, only 1 time out of 8 will you get an agreement about what a penguin is, right? If you randomly select two people and have them have a conversation, only 2% of the time will the conversation end when both parties want it to end, and only 30% of the time will it end when one of them wants it to end. We're not good at understanding what other people know or think. We're wretched at it. Okay, so I'm going to go ahead and open this tab, and I'm going to try and turn this thing on, because it should be on. Okay. Give me a second. Oh, yeah, hang on. Let me do it in the other browser. Just take a moment. So I thought I had that turned on. Not right now. Okay, we'll have to do it later. That's fine. But you're going to add more bits of terminology, and you're going to add their definitions for various disciplines and subdisciplines and subdisciplines and so on, so that we can build a shared glossary. All right, so now let's move on to the next issue, which is, are enterprise IT and research computing natural enemies or natural allies? And oddly enough, I find myself in a very weird position. I am a natural pessimist. In fact, I'm a pessimistic cynic, or perhaps a cynical pessimist. But here I am very much an optimist. I believe that enterprise IT and research computing are natural allies. And certainly that's how it's worked out in my career. Okay. But you have to start with the understanding that research computing is qualitatively very different from enterprise IT. On the other hand, enterprise IT is approximately all of IT, and research computing is approximately none of IT. So we're the weirdos. We're the mutants. Okay? Let's be specific. And I was just having this discussion in the last hour in a meeting. Okay. So if I had to distill enterprise IT down to a single concept, it would be 5 nines. So 99.999% uptime. That's 5.25 minutes of downtime per year is the target, okay? Target for enterprise IT. Yeah, okay, if you get 4.5 nines, that's like half an hour of downtime per year, you're probably still okay. But if you're at 4 nines, you're fired, right? That's several hours of downtime per year, and you're gone, right? So everything has to be secure. It has to be best practices. It has to be established technology. By the way, in the world of technology, you always have exactly two choices. You can have established technology, which means obsolete, or you can have new technology, which means broken. So on the research computing side, we tend to be in the broken technology business, okay? So that's your goal in the enterprise IT world is secure, established technology, best practices, 5.25 minutes of downtime per year. The research computing side is the exact upside down of that. Research computing is, and I'm not making this up, 1.5 nines, 95% uptime. What that translates to is about 18 24-hour days, 438 hours of downtime per year. That is, it's either 4 or 5 orders of magnitude more downtime per year than 5 nines, right? And I'm not making this up. This is straight out of year after year. NSF's large solicitations for 8 and 9-figure supercomputers. This is their wording, and it's been repeated over and over, so clearly this is the standard. Production resources should be unavailable as a result of scheduled and unscheduled maintenance no more than 5% of the time, meaning up 95% of the time. So what do you need to be in research computing? You have to be fast and flexible. You got to be able to turn on a dime. So if we don't have a capability today and a researcher comes to us and says, I need such and so capability, if we're lucky, we have a week. More commonly, we have till tomorrow, right? And just because it's 7 p.m. tonight doesn't mean we get past tomorrow to get it up and running, right? It's got to be cutting edge technology. If it's cutting edge, by definition, it's broken, right? We don't know how to use it. And the software, the drivers or the software packages, whatever, hasn't really figured out, hasn't been debugged against it. So it's guaranteed to be broken. The vendors send us pre-broken technology for our convenience, and then we work with the vendor to get the technology in good working order. And in many cases, there's just plain no such thing as best practices. There's no such thing as a standard cluster supercomputer architecture. Every single one is a one-off, right? And that's good, but it creates some challenges of its own. So here's an example of that. In summer of 2016, so this is now, what, 8 years ago, 9 years ago, Delta Airlines had a 5-hour outage in their primary data center in Atlanta. It was a power problem, I believe. It cost them, by their own public report, it cost them $150 million. That's $1 million of loss for every 2 minutes of downtime. Now, if my institution goes down for 5 hours, it's not going to be $150 million worth of loss, but it will be proportional, right? So if some mission critical capability is needed tomorrow, let's say payroll, if tonight is the night that payroll runs because tomorrow is payday, but tonight the machine that runs payroll goes down. Now, happily, we do payroll in a VM, and so it can migrate among many physical machines, but never mind. What's going to happen to the enterprise IT folks who are responsible for that tomorrow? Well, heads are going to roll, right? Or assistant heads anyway. So enterprise folks, they have two choices. They can achieve the 5 nines or near enough to, or they can sell pencils out of a cup. That's it. Those are their options, right? Either do that or get out of the business. On the research computing side, there's no such pressure with respect to uptime. The pressure is to be cutting edge, to create and provide new capabilities, right? Because otherwise, proposals and research coming out of your institution is less competitive. And it's not that if you aren't cutting edge today, you're fired tomorrow. It'll take time for people to get sufficiently angry to want to fire you. But if you don't stay cutting edge, over time, you'll put yourself out of business. So how do we resolve this discrepancy? Well, the beauty is that research computing, unlike enterprise IT, research computing can afford to make mistakes, because if a mistake leads to a day of downtime, that's an annoyance, not a crisis. And here's the way to measure it. It's again about the cash. It's about the money. Okay, so imagine you have a full 24-hour day of downtime on your university's supercomputer, right? What does that mean? Well, on our machine on any given day, 10 to 100 people are running jobs. But who are those people? They're not faculty, right? Because faculty really get very little time to actually do research tasks. For the most part, the people running jobs on our supercomputer are grad students. Faculty do research management. They write proposals, they help their students and postdocs write papers, they hire the students and postdocs, they teach them how to create posters, how to contribute to writing a grant proposal, whatever it may be. But they're not spending a lot of time on research tasks. They're not getting their hands dirty because they don't have time to do that. They'd love to do that. They just don't have time to do it. This is why they so jealously guard their sabbatical. You know, they get a semester, or if they're lucky, 2 semesters off every 7th year to go actually do research instead of just research management. So who's really doing the research? It's grad students and postdocs and undergrads, but on average, it's grad students. Well, what's a grad student cost? At the high end, you're looking at including indirect and fringe and tuition support. You're looking at something like 60K. So 30K salary, and then that doubles with what we call fully loaded with those other components. So grad students worth 60K. So 100 grad students down for one day translates to about $16,000 worth of productivity loss, right? But then you slice and dice it by those 10 to 100 grad students are from 5 to 50 different research teams. So the way you're going to get there, you're going to be slicing and dicing by research team. An individual research team's loss is going to be between low 3 and low 4 figures for a 24-hour downtime. So that's not really a crisis. That's an annoyance. Now, would faculty like to have 5 nines? Of course they would, until you explain to them the trade-off, because the trade-off is cost. So to get from 1.5 nines to 5 nines, you have to increase the cost per unit of computing, per unit of storage. You have to increase that cost by on the order of a factor of 10, right? But if that happens, if I go to my boss and say, okay, I'm going to get us from 1.5 nines to 5 nines, it'll cost 10 times as much. So can you give me 10 times as much budget? He'll get a good laugh, and then he'll gently show me the door. We get along beautifully, but that would be a little over the top. So if I want that, if we want to provide 5 nines for our researchers, the cost is 90% of their research productivity. I actually once offered that to not our current CIO, but a predecessor. I offered it to a faculty member in front of a predecessor CIO. I said to the faculty member, if we could get you 5 nines, 5 minutes of downtime per year, would you like that? And he said, oh, absolutely. And I said, what if the cost of that was you'd have to give up 90% of your research productivity? He said, not if you live to be 1 million. So let the machines go down from time to time in exchange for much greater aggregate research productivity. Because after all, faculty are not judged on research productivity per day. They're judged on research productivity per year. Okay, and we had a comment, previous slide. Second set of bullets assumes a sane and predictable. Yeah, we're not going to get into the politics of that. But it is always true that if you don't have good research computing, you are less competitive than those who do. Okay, so how much failure is normal? So I ran the numbers on our supercomputer, right? So we ran about 17.5 million jobs in calendar year 24. About 1.3 million failed. Not quite 8% of all jobs failed for one reason or another. Of those 1.3 million jobs, 83,000 of them failed because of server failure. And actually, even that is a wild over-exaggeration because it was not typically physical failure of the server. It was usually either a kernel panic was induced, so it was an operating system problem, or the most common, the users were consuming more RAM than was available, and so their jobs started to crash because we don't provide a lot of virtual memory on disk because then everybody's job slows down by a factor of 1,000. It's not worth it. Better they crash. So failure of batch jobs on supercomputers, totally normal. Happens all day, every day. It's no big deal, right? Almost 8% of jobs failed. So let's call it one job out of 13. Every 13th job on the supercomputer failed. Almost none of them failed because there was a physical problem with the hardware. So what are the implications for IT as an organization? Research computing costs a lot less per unit of computing, per unit of storage than enterprise IT, but it's also a lot less resilient, a lot less reliable, a lot worse uptime. So if a researcher comes to us for help, one of our first questions is, can you tolerate roughly 8 hours of downtime a month? And if the because we run closer to 2 nines, we're at about 98.8% uptime. Because if the answer is yes, I don't mind having 100 hours of downtime a year, give or take, then research computing is where they should be because of cost. But if their answer is no, we can't tolerate a significant amount of downtime, then the answer is go to the enterprise IT side, which is much more expensive, but will meet the need. We actually had a research group once say, well, this stuff over here, 2 nines is fine, but that stuff over there has got to have the 5 nines, right? Great, split off. Okay, the mindset gap. So in the golden olden days, 20 years ago, in the distant mists of the early 2000s or the mid 2000s, we used to say that a typical new user would come to us from a Windows or Mac OS desktop or laptop background, right? They were comfortable using that particular kind of machine, and we had to get them from there to using the supercomputer, right? And again, the supercomputer is a completely different animal. It's command line Linux, batch, remote, shared, okay? But nowadays, a typical new user is coming to us from an iOS or Android background. So how did that change our job? Well, the mental distance between your phone versus a supercomputer is even bigger than the difference between your laptop and a supercomputer. So on your phone, how do you install software? And we mentioned this before, 3 taps, right? Once to open once to turn on your phone, once to open the store, once to open the store, once to download the application, and once to give it permission to listen to your phone calls, right? Very easy. If you're on a supercomputer, what do you got to do? Well, if you are very comfortable with Linux and with installing open source third-party Linux packages, because they all do it differently. There's no install wizard for most of these packages. Then you're going to be doing that by hand. Otherwise, if you're a sysadmin, you might be running Easy Build or SPAC, if you're lucky that particular application already knows how to be built by those. Our users are not going to be doing that kind of stuff. Some of them, sure. Most of them, no. They don't have that skill set. So we got to prepare to help them with that or do it for them. How about storage? Well, on your phone, if you want to increase the storage, it depends. If it has an SD slot, you can go to your favorite big box store and you can buy a little micro SD card and stick it in there. It will be immediately recognized within seconds. And you can start moving data, to your SD card. If your phone does not have an SD card slot, the way you upgrade or increase the amount of storage is you buy a new phone with bigger storage, right? And any of those, if you're buying an SD card, you're looking at 2 figures. If you're buying a new phone, you're looking at 3 to low 4 figures, right? How do you do it at large scale? And some of us have done this, have been through this. Okay, so first you have to design what you need. Then you write the text for the RFP, the request for proposals. Maybe first you do a request for information to have some starting information about it. Then you do the request for proposals, and you might give people several weeks or even multiple months to return their bid responses. Then you have to evaluate the bid responses. Depending on the size, you might have to go to your institution's governing board to get permission to spend the money. And that could occur before you do the RFP or after or during. Any of those is a possibility. Then you have to configure the system you actually are going to buy. Then you purchase it. Then you have to deploy it, which is both physical deployment and configuration at the keyboard level. Then you maintain it, which means you're always keeping an eye on it. You may expand it. And ultimately, when it gets to end of life, you decommission it, and you have to ultimately physically remove it from the building, wherever it is your institution sends it. Just getting it up and running is going to take months, could even take years, right? Its full lifetime is going to be many years and is always going to involve you giving it your attention. It's a huge mental distance from I stuck a card in a slot and now I forget about it, right? What does a storage cost? For a handheld, you're looking at tens or at worst hundreds of dollars. For a laptop, kind of similar. Terabyte, that'll get you terabytes of spinning disk or high gigabytes, low terabytes of SSD. At the large scale, you're looking at, for tape, you're looking at thousands of dollars per petabyte. For spinning disk, you're looking at tens of thousands. And for SSD, you're looking at hundreds of thousands per petabyte, right? And for large scale resources, petabytes are normal. Okay, why else is it hard to use research computing? Well, part of the issue is the mindset gap, but then on top of that, research computing systems are getting harder to use, and they're getting harder to use in two different dimensions. The storage hierarchy keeps getting deeper. So think about what the storage hierarchy is today. You've got, inside the CPU, you've got registers, and you've got 3 levels of caches. Then you've got, on some systems, you've got HBM, high bandwidth memory, and then you've got traditional server RAM, and then you might have multiple levels of SSD. So you might have, for example, the CXL stuff that's very fast, and then you might have some NVMe, and if you really need a lot of capacity, but you don't have big budget, then maybe you're going to have some SATA in there to get the capacity. Okay, so now you've got that, but then for the really big stuff where you're getting into petabytes, you might not have the budget to do that on SSD, so that's going to be spinning. But then if you've got hundreds of petabytes, you might not have the money for that in spinning, so then that's tape, right? So there's this huge, and that's just today. The storage hierarchy keeps getting deeper. So have no fear, this will be harder later. Yes, so presumably the tape or at worst the spinning disk would be your backup system. Okay, would include your backup system. Okay, but then the other dimension of this, in addition to research computing is always getting harder to use. Oh, and I neglected to mention parallelism. Parallelism keeps getting more hybrid. So in the olden days, you did MPI, and you could talk across multiple servers, which was important because a typical server had 1 or 2 or at most 4 cores. But then along came OpenMP because now servers had 8 or 16 or 32 cores. And then along came GPUs and other kinds of accelerators like field programmable gate arrays and so on. And you've got to have more and more sophistication to how you handle the parallelism in your software. So it becomes harder and harder to use. Now, on the other hand, more researchers need research computing, and that's again in 2 dimensions. More disciplines need research computing. So in the olden days, I didn't hear from English faculty saying, I want to do a textual analysis using a large language model, right? But on the other hand, a higher and higher fraction within each discipline needs research computing. And of course, that's compounded now with AI and the rise of large language models. More and more researchers are wanting to adopt AI into their research. Okay. Let's move on. So we now have a feel for the circumstances we find ourselves in. Now let's talk about the researchers. And why are they that way? Okay, we're going to break it down. Faculty, staff, students, and we'll break some of those down into smaller things too. So what do faculty get rewarded for? Really, at almost any academic institution, the three things they get rewarded for are not necessarily in this order: bringing in money, publishing papers, and graduating students. If it's a primarily teaching institution, it's in the exact opposite order: graduating students, publishing papers, bringing in money. If it's at a research intensive institution, it's going to be in the original order I quoted: bringing in money, publishing papers, graduating students. Different institutions may have different orders than this. That's just a generalization, but that's a generally good way to look at it. So if that's true, then how do we both take advantage of that and avoid all the difficulties, or at least minimize the difficulties associated with that? Part of the problem is faculty are not rewarded for having good IT. In fact, they're implicitly punished for having good IT, in the sense that any money or time they put into good IT is time and money they could instead have put into, for example, hiring more grad students to do more research, publish more papers. So they're implicitly punished. They get less reward when they spend money on good IT. So they would prefer to spend nothing, but if they can't spend nothing, then they'd like to spend as little as humanly possible to pay for their computing and storage. And by the way, their mental model for what computing and storage are supposed to cost, if it's not zero, which is what they prefer, if it can't be zero, then it's supposed to cost the same as USB drives from Walmart. So you're looking at 20, 25 bucks per usable terabyte per copy for a period of, let's say, 5 years, right? Of course, that's not something that we're able to deliver at scale. And putting your research data, your mission critical research data, on USB drives and sticking them in a cardboard box, maybe with a one-word dino label on them or something, not only is not a good idea in real life, it also will get your data management plan crushed, in which case you won't get the grant. So we need to be able to provide them with something that is good, but still reasonably affordable. Okay. Now, let's start breaking faculty down. Tenure track. So people who do not yet have tenure, right? So what's their incentive structure? They got hired and they were told, typically, you have 7 years to get tenure or you're out of here. Okay, well, 7 years. I got 7 years to do the research that's going to decide the rest of my career beyond that. 7 years. And if I can't deliver enough, I'm fired, right? So I've got to have my stuff working now, and it has to keep working reliably. And by the way, that 7 years, it's not really 7 years, because year 7 is the courtesy year, where that's your year to transition to a position somewhere else because you're not getting tenure. So it's really 6 years. Well, except that year 6, that's the year you put in your tenure package, and it takes about a year to evaluate your tenure package to see whether to give you tenure, right? It has to go out to external reviewers. It has to be reviewed by faculty from multiple different departments at your own institution, et cetera, et cetera. It's a very lengthy process. It has to go through multiple layers of votes, right? So your department's executive committee votes, then your department's entire tenured faculty vote, then it goes to the faculty senate, then it goes to the provost, then it goes to the president, then it goes to your governing board. And I probably have left out a few layers in that. All of that takes time, and it has to be done in the correct order, right? So, all right, so I don't have 6 years, I have 5 years, okay? Because year 6 is when I'm going to be evaluated. But the problem is, any paper you submit to a journal, it's going to probably take on the order of 6 months to get it published. So from the time you set foot on that campus to the time you have to be done with the research that will decide the rest of your career until you retire, it's 4.5 years. That is an enormous amount of pressure to be under. Okay, but let's say you do get tenure, right? There's a couple of problems. One is you already have the mental habit, right? Everything has to work now and forever. right? Because I got to be able to do my stuff and I don't have time to wait around for you to fix things. Okay. And I don't have time to learn how to do anything either. It's got to work and it's got to be easy to use. If you're tenured, you no longer have that sword hanging over your head, but you've still got to have the same kinds of accomplishments if you want a raise, if you want a promotion, for example, from associate to full professor, if you want a named chair, if you want whatever other prestigious outcomes like joining one of the national academies, whatever it is, still the same. I need things to work now and keep working reliably. Okay, what if you're research faculty? You're not even on tenure track. Well, research faculty live on soft money. If I don't sing for my supper, if I don't bring in enough grant money to pay my own salary, I don't eat, right? I get laid off. Okay. In order to bring in the grant money, I've got to have a lot of publications. I got to be publishing a lot. And because I don't want to be a research faculty member forever, I want to get a hard money position. Because of that, I need a track record of graduating students, publishing papers, and bringing in grant money so that I can apply for tenure track positions on hard money, presumably at other institutions. Although if there's something that opens up at my institution, I'll probably apply for that too, because I don't want to live on soft money forever. Right? When you live on soft money, you never know where your next meal is coming from. Okay, well, what about a postdoc? Well, okay, so I need to learn how to be faculty. That's why I'm being a postdoc. So I've got to publish a lot, or I'm not going to continue to be a postdoc and I'll get fired. But I need to learn how to get grant money, and maybe even learn how to train students to do research so that when I go to apply for a faculty position, I will have the skill set and I'll be able to demonstrate to the faculty committee that's doing the hiring that I'm worthy of that position, that I'm competitive to that position. Okay, what about students? If I'm a student, my number one goal is to graduate, right? So anything that delays my graduation is costing me money. And I actually ran that calculation in the late stages of my grad school career. And I realized that based on foregone salary and benefits, not even thinking about sort of accrual of interest on savings or bonuses or whatever it might be, just the salary that would have come in, thinking about what bachelor's entry-level positions were getting when I finished my bachelor's degree, I figure that my PhD cost me between $250,000 and $500,000 straight up, right? So any time that you spend as a student is costing you money. So of course your goal is to graduate. So everything has to work reliably the first time and forever. All right, let's talk a little bit about research funding. What is the academic research funding model? Here's what a grant is. A grant is a random amount of money that shows up on a random date and is available for a random duration, right? So you put in a proposal and you say, here's how much money I want, here's when it should start, and here's how long it should run. And then the funding agency can totally ignore that and do something completely different. Usually they'll be pretty close to what you ask for, but there's no obligation. They can do whatever they want, right? And grants fund most academic research, right? Grants tend to strongly favor researcher salaries, and they strongly disfavor anything that is not researcher salaries. Okay, they'll pay for a bit of travel for the researchers to go to conferences and whatnot, but that's about the extent of it, right? And they disfavor things that are not researcher salary. And by the way, salary, fringe, indirect, but I'm simplifying. Disfavor equipment, services, non-researcher staff, right? And researchers don't really get credit for the stuff that grants disfavor. And recurring charges are really hard to sustain over the long term. Now, there are institutions where you can do it. If you're at a top 25 institution, maybe a top 50, but definitely a top 25 institution, you probably have literally more money than you know what to do with. That is, there's an upper limit to how many students and postdocs an individual faculty member can manage. And it varies by faculty member, but let's say on average it's 10, right? At a non-top 25 and certainly a non-top 50 institution, maybe I should say that the other way around, but at a non-top 50 institution, you probably have way less than 10 students and postdocs on your team because you can't afford them. You don't have enough grant money. So in that case, any money that comes in, you want to spend on researchers anyway, right? And the problem with the top 50 is there's only 50 of them, right? Out of 330 some R1s and R2s, let alone, I think, 2,000 primarily undergraduate institutions, or at least non-PhD granting, maybe is a better way to say it. Okay, so if you've got, let's say you put your data in a commercial cloud, you've got a 3-year grant, that's great. And for 36 months, every month you're paying the monthly fee for your data. And then in month 37, the vendor will have no choice. They'll have to delete your data for you, right? Now, in theory, the next grant could pay for that, except the problem is that the data for this grant probably isn't that useful for the next grant. More often than not, it is not useful. So you can't justify paying for the old data on the new money, right? Now, some academic institutions have big endowments that include significant internal funds to support faculty's research programs. But again, that's largely true at top 50 or maybe top 25 institutions. And again, problem with the top 50 is there's only 50 of them. All right, what's your probability of success? For the NSF, because that's the one where I know to find the data, it's typically on the order of a quarter of grant proposals get successfully funded. It varies by directorate, it varies by state, but it's still a law of large numbers game. If you want to get one proposal funded, you should expect to submit 4 proposals and have 3 of them declined, right? Okay. How does research computing get funded? Well, it's a mix. At most institutions, some subset of the following are relevant. So internal funds on a regular cadence. So at my institution, we get an annual budget. It pays both for people and for things. It doesn't pay for all, but it pays for a significant fraction. Okay. You might get internal funds at a random time. So you go to the higher ups and say, we should buy a supercomputer. And they say, sure, here's N million dollars, right? Go buy a supercomputer and don't come back for another 5 years, right? Grant funds can come in at random times. So you submit a major research instrumentation proposal to NSF, or you submit a CC Star Compute to NSF, or you submit a Defense University Research Infrastructure Program, I think it is, DURIP, and that's a chunk of money to buy a machine. Or I can't remember the name of the NSF's, the NIH's program. I think it's SIG or something like that. They all have programs, or a lot of them have programs where you can buy a machine, right? A chunk of money comes in, you buy a machine, you're in business. But you can't do that every year as a general. For public institutions, you might get a state appropriation. That might come in random years, right? So once in a while, the state creates a line for what you're doing. Historically, at my institution, we have avoided that because that would be the first thing that would get cut in a tough budget year. So it's much better to have that a bit closer to home where people can see the value of putting the money. You can do usage charges. That's not that common. Per core hour charges are unusual in our business. Faculty really don't like them as a general rule, unless they're very, very low, substantially less than cost recovery. Many institutions operate on a split model of condominium, meaning machines researchers buy that then become part of the supercomputer, and internally funded. They're available to everybody at no charge. And that split model is probably the most common, and it may have some of these other elements as well. Usage charges is not very common. Also, some institutions like to lease large equipment, others like to buy large equipment, and some even do both, right? So what's a good way for faculty to spend their time? If we believe in bringing in grant money, publishing papers, graduating students, and that at some institutions, that's the order of preference. Do we want them writing grant proposals, and I'll put grant in scare quotes, writing grant proposals whose purpose is to get time on the local supercomputer? So at OU, we decided the answer was no, because we figure they have a limited number of hours per year that they can spend writing grant proposals. We would much rather that they spend their grant proposal writing time getting money from outside the university, bringing money in, than getting permission to use a machine that's already paid for. All right. What to say to a researcher to make them want to work with you? So with regard to cost, here's a way of doing what you want to accomplish that is cheaper than the way you're currently doing it or the way you plan to do it, right? Or a modified version of that, for the same dollar cost, here's how much better it could be if you go in with us, right? Control, you get to decide how to use your part of it, right? The thing you pay for, you get to decide how to use it. You can share it with whoever you want, right? Your students will not have to spend their research time taking care of research equipment, or at least not this research equipment. Okay. How to find researchers. Okay. Where do you find them? So I just went through a round of this because I'm writing a proposal right now, and I didn't do it for my institution because I already have that list pretty much locked down from just people requesting accounts. So I have a giant spreadsheet out of our system where they do account requests, and I can trivially look up who the PIs are. So for my institution, that's very straightforward. It literally takes 5 minutes. But for other institutions, because I'm doing a project that involves other institutions, I go to their institutional website. I click on academics, right? That takes me to the list of departments, or sometimes the list of degrees, and then I can drill down to the departments. I go to the department websites, and I look for faculty or people or whatever the link is, and then I read their research descriptions. Because that's where I find out who's doing research that might get value from research recruiting. So what keywords do I look for? Computational numerical, that's especially popular in engineering. Parallel, you usually see that in CS. Informatics, that comes up in a number of contexts. If it's specifically the chemistry department, you can look for computational chemists. You didn't used to be able to do this. In the olden days, by this I mean maybe up till about 2015 or so, computational chemists would not label themselves computational chemists. I think because their non-computational colleagues kind of looked down on them, so they would call themselves physical chemists. And they were computational physical chemists, but they didn't include that word. In chemistry, I looked for those, but I also looked for the word calculation, or calculations, plural, because that's the word they use for doing computing work, which seems like a perfectly reasonable word to use, but you almost never see that word in engineering in their research descriptions, which is interesting to me. But computational chemists, now you will find people who genuinely label themselves as computational chemists, physical chemists, biochemists, right? Does anyone feel AI may do our work soon? If you're talking about this kind of work, going through the exercise, and by the way, it took days to do this. Going through the exercise, I went to, I want to say probably 20 universities' websites. Going through that exercise took days and days. And by days, I don't mean like an 8-hour business day. I mean 12 to 16 hours a day for several days. It's mind-numbingly dull work, but it got to get done, so you do it. I don't think AI is going to do it. No. And the reason I don't think AI is going to do it is because I don't think AI has the fine-tuned control to drill down to specific faculty in specific disciplines that have randomly differing names. So, for example, and this is kind of cool. There was this thing that came out many, many years ago about if a language has a name for only one color, it's white. If it has a name for two colors, they are black and white. If there's a third color, it's red, and so on, right? And there's a whole list of them, what colors and what order they come in, right? The same principle applies to academic disciplines. So, if it's a small institution, there isn't a physics department, there might be a biology department. That's the most likely thing. If there isn't a physics department and there isn't a chemistry department, then there's a physical science department that has both of them. Or there could be a natural science department that has all three. There's almost certainly a math department, but it could be a math and computer science department. Now, on the other hand, the computer science department might be in the business college, right? There's such variety in how these things can be arranged that if I expected to be able to send a bot out to do it for me using AI, I would find myself horribly disappointed. No, I do not expect that bots can do this, that AI can do this for us. It's too fine-grained for what they seem to be well-positioned to do. Okay, now you've tracked down these faculty by looking for these keywords, by visiting a zillion web pages. What do? You contact them. Just send them an email, cold email. Tell them what your role is. If it's for a grant proposal you're writing, tell them about that, right? What program are you submitting to? What the due date is? How much money? What's it about? And ask them, do you need this kind of large scale, high performance, whatever it may be, computational or storage or network or whatever? Do you need this kind of capability, right? Then go find them where they're at. So most institutions have like a regular new faculty event, right? Where they get together once a month or whatever, and they talk about how to be good faculty, how to be effective faculty, right? So go to those, arrange with the people who run those. I'd like to come do 5 minutes about how swell our research computing is, and they'll often give you a free lunch with that. So that's pretty groovy, right? You go to where they are. So here's another trick that I figured out. I don't do it as often as I should, but from time to time, I will pull up the minutes from our governing board, our Board of Regents meetings, and they have a section on new faculty, and I'll just go there and quick read what discipline are they in, and then I'll go look them up and see, is this person a good candidate? Right? Could be, right? And then just send them a cold email again, right? By the way, many of you have heard this from me before, but for those of you who are here for the first time, you will hugely increase the probability of response by putting their first name at the top. And if they have a nickname and you use the correct nickname, that's another big boost beyond putting their non-nickname. So if their name is Elizabeth, but they go by Liz, and you put Elizabeth at the top of the email, that's much better than not having a name at the top. But if you put Liz at the top of the email, that's really going to help with getting a response from them. This is why, by the way, when you registered for this event, I asked you what your nickname was, or one of the reasons anyway. And then go visit them, right? Even better, take them to lunch, right? Now, if you can get your institution to pay for that lunch, that's ideal, but maybe you can, maybe you can't. There's something magical that happens when human beings are physically together, and that magic is amplified when you share a meal with someone. I don't know why. I don't pretend to understand any of the psychosocial magic that happens. But this is why, for example, many of you have experienced that vendors, people trying to sell you products and services, want to come visit you. And ideally, they'd like to take you to lunch. Why is that? Because the psychosocial magic that happens when people are in the same room together is enormous. It makes people trust you more. It makes them believe in you more. It makes them like you more. It makes them more willing to take a risk on you. And if you share a meal with them, and you don't have to eat the same food, you just have to eat at the same time at the same table, then that's amplified even more. So if you can take somebody to lunch, that's a giant win, right? I had an appointment with an institutional officer last week, and it was supposed to be Zoom only. And I went to the building next door to where their office was, and I sent a note to their admin and said, since I'm next door anyway, could I come in person? And they said, sure, instead of doing the whole meeting on Zoom. And it worked way better, way better. So you're visiting this faculty member, you take them to lunch, whatever. At a high level, what is your research about? Tell me about your research. Actually, the way I like to couch it is tell me about the computing and data intensive aspects of your research. Because usually they can really talk about that. And honestly, I'm not going to understand when they start talking about the surfactants and all this stuff. I'm not going to understand. Right? It will get them talking and animated, and I'll be able to judge what do they think is important? What are they excited about? What matters to them? Because that's really the valuable information. And then my favorite thought experiment. Suppose you have an infinitely large, infinitely fast computer. Then what research would you do? Because then I've got them thinking past the sale, so to speak. We've got them thinking about what's the end goal for my research, and then work back to what we can accomplish now, rather than just start from where we are today, because that doesn't give them anywhere to go. Okay. So I'll get the permissions fixed on this webpage, but add a piece of terminology that's used in a specific discipline or subdiscipline or sub-subdiscipline or whatever. How it's used in that one, you can look at one that's already there and add a new discipline. You can add a new term and list one or more disciplines for it, but we'll build a shared glossary together. We've been doing this for several years, and I think it's been immensely helpful. Okay, questions. And I got about 4 minutes. And I know there was a lot of discussion in the chat. I didn't have time to work my way through it, unfortunately. Google's AI co-scientist cracks research problem in 2 days. Do you want me to take out the dollar? I'm going to take out the dollar now. Who wants the dollar? One crisp, shiny dollar for asking me a question. Okay, someone has popped up a question here.
Henry,
Yes, go ahead.
hi, this is Vinod from Colombia. Thank you very much for great talk. I'm sorry if I missed your earlier part of the presentation,
No
but
worries.
my question, you mentioned the condo model where faculty can bring on their own hardware. Do you see some problems with mixing the hardware? Everyone comes with their own specs, etc.
So every
You have to
institution
manage
does
it.
this a bit differently. The way we do it is we have to get them the quote, and it has to be from our preferred vendor. They can have whatever, well, okay, within limits. So we have categories. So we have sort of a generic compute node, and we do an Intel version, an AMD version. We don't do ARM. We only do x86. So we put limits on it, right? Here's ways that you can do the network. You can have a 3 or a 5 year warranty. We strongly urge 5, but we'll allow 3 if they really, really have their heart set on that. They can set the amount of RAM. We do put the guardrail of you have to fill all of the memory channels equally so that you get the best possible memory performance. And once in a while, we can even get an exception to that if they have a compelling reason why. So I agree with you. What you don't want is for them to go to a random vendor who happens to have the best pricing that day on a random collection of components that has no resemblance to the rest of what you have. I agree 100%. So we do put guardrails around what they're allowed to buy and who they're allowed to buy it from. And ultimately, we get them the quote so that we know that what they have a quote for is compatible with the rest of our equipment. But within that constraint, there is a lot of room for variation. Is that more or less the question you were looking for?
Yeah, that's exactly right. I mean, I had difficulty in talking to faculty members. They try to save every dime. So they often end up, if you don't specify the specs and you say that this is the vendor, this is a configuration only you can buy, they end up buying something which is dirt cheap. And then it becomes your problem to maintain it for next 5 years.
Right. So one of our approaches on this is if you went off and bought something on your own, it's your problem, not ours. If you didn't come to us and work it out with us, and we actually have a web page where we list options, right? If you didn't come to us and work it out with us, we're not going to adopt it into the supercomputer. And we're very explicit about that. You have to do it with us. Okay, hang on. There's traffic in the thing here. Know anyone who also speaks the student who would translate? Hang on, I missed the starter question here. Let me. Um, I'm losing the thread of the thing. Okay. Question about clarity of communication. Do you have any tips dealing with students who don't speak English as a first language? I get some who only understand every third sentence. Yeah. So I don't know that I have tips exactly, but there's going to be a lot of variation in a speaker's background with whatever the local language is. And you know, in the US, it's going to be English. But we got people from all over the world participating in this. So there's going to be different levels of experience and facility with the language that the facilitator speaks. That is the nature of any kind of position, especially in academia, where you draw faculty, staff, and students from all over the world. And honestly, my advice is the more you practice talking to people from other parts of the world who speak other languages and who learned your local language later in life, the more you will be skilled at learning to listen to them. And one of the things that really brought this home for me was when my kids were really tiny and they were just sort of starting to speak. And my mom would come and visit, like for a month at a throw, 2, 3 times a year. And she would report to me that she didn't have the faintest idea what the kids were saying. She couldn't understand a word they said. And I understood everything they were saying pretty much without any difficulty. Why? Because I had practiced listening to them. And I find that the more that I talk to an individual, the easier it is for me to understand what they mean. And the more that I talk to a group of people with similar accents, the easier it is for me not only to talk to them, but to new people who come along who have the same or a similar accent. And so honestly, my best advice is practice talking to people who your first language is not their first language, because that practice will pay off over the entire course of your career. There will never be a downside to having that practice and building the skill of understanding people who don't understand you. Now, that's half. The other half is, how do you get them to understand, right? When you say something, how do you get them to understand? First, I find it's very different between writing and speaking. With writing, I have found the bigger the words you use, the higher the probability they will understand. Because when you use small words, the problem is you're more likely to use idioms. You're more likely to use phrases that only exist in your language and do not exist in their language, right? And that can be very challenging. Whereas if you speak journal speak, so to speak, if you speak expository writing language, when you're writing to them, if you use the big words, they know the big words. They use them themselves. Whereas that they may have much more hesitation around the phrases that you build with small words. So one thing that I notice, for example, is in English, we often will drop a pronoun. So we'll say, great idea, not that's a great idea, right? You can imagine how confusing this would be for someone coming from another language, that you're dropping words. They don't know what words you've dropped because they're not accustomed to this behavior. When you're speaking, you often don't enunciate certain phonemes. So for example, instead of saying isn't, you might say int, right? Or instead of saying give me, you might say gimme, right? This is normal behavior, and many languages have habits like this. So what you have to learn to do if you want the person you're talking to understand you, and if they're struggling with that, is you have to enunciate more carefully so that they can translate that into something that makes sense to them. You have to be very careful about idiomatic usage, both in writing and verbally. It's more of constantly ask yourself the question, how would they know about how I'm using that word? Is there a way I can say this that is more book and less hanging out, right? How would I talk to a customer instead of to my buddies? Those kinds of issues, I think, really feed into how can I communicate more effectively with the researchers who I'm trying to facilitate for. Did that answer that question?
If I may ask another question about
Sure.
condo model. I mean, how do you get the fair value of your investment? I mean, if you reserve their nodes, then it's not very efficient because others cannot use it, the unused cycles. Now, if you put in the pool and the faculty member has to wait in the queue, he'll say, "Oh, I'm not getting my value of my out of my investment." How do you deal with that?
Right. And I have a couple of answers. Um, the one thing to bear in mind is that you're balancing the trade-offs, right? So you're not going to get a perfect outcome. The perfect outcome would be every core of every node would be 100% utilized all the time. You will not achieve that, right? Let's start from that. Perfect is not an option. So let's not make the perfect be the enemy of the good. A significant fraction of researchers will not buy into your condominium model if they don't have confidence that when they submit a job, it will start immediately, unless somebody in their group is also running a job, right? If it's their group that's consuming the resource, they don't mind waiting. But if it's a third party, why would they spend money if some third party is going to come in and take over their machine? Some institutions have a strategy for this where in the condominium queue that is using other people's condominium nodes, you can submit to it for general purpose use, but your job can only run for 6 hours or whatever. So the owner is guaranteed that their job will start within 6 hours. Other institutions, and my institution's approach is it's your machine, you paid for it. We're maintaining it for you at no charge, but it's your machine, you paid for it. You get to decide who runs on it when, right? We don't tell you. A variation on that theme would be anybody's jobs can run on your machine, but only in killable mode, that where one of your jobs enters your condominium queue, then their job automatically gets killed off within, at worst, minutes, but ideally seconds, right? We haven't been doing that on the condominium side. We do actually do it on the general use side, the non-condominium side. It only works for a very limited set of users because many applications can't be done that way. There isn't really a good general purpose auto checkpointing capability. There are a couple of technologies. One of them doesn't do MPI, and the other one doesn't get enough funding in order to be able to prove the level of reliability that our researchers would insist on. But there are certain classes of applications that we're currently experimenting with, and one of them is AI. So TensorFlow and PyTorch and such, they do have checkpointing that you can write into the software. And so we can work with users who have very large training jobs to do and say, you can run for unlimited duration in this special queue as long as you have turned on auto checkpointing the way we require, and other users can come in with shorter inferencing jobs at any time and pause your job, which really means kill it and resubmit it, resubmit your job, and then your job will restart from the most recent checkpoint. So there isn't an all-inclusive simple answer to your question. There are a variety of approaches to get better utilization without getting great utilization. And there are a variety of approaches to get great utilization, but that drive down the attractiveness of the condominium offering because researchers want on demand if they're going to pay for it. It's a balancing act based on what your institution is willing and able to do.
Yeah, good answer. But can I ask what's your ideal goal for utilization?
I don't have an ideal goal. The problem again is that we are balancing trade-offs. My ideal goal is that we balance trade-offs in a way that minimizes faculty discontent, and research non-productivity. And I'm going to flip that over and say it in a positive way. We want to balance the trade-offs such that we maximize faculty delight and research productivity. That is not the same as maximizing utilization percentage. Okay, so let's wrap it up. Thank you, everybody. Our next session will start in, I believe, 50 minutes at half past the hour. So we look forward to seeing you there. And that next session, I believe, is CI user support. And I believe our presenter is Chris Reedy. So we look forward to seeing Chris 50 minutes from now. I'm going to leave the Zoom session open. I'll have to pass it off to someone else because I've got to move to a different building. But we'll see you all. Stay logged in, and we'll get started on the next one right on schedule at half past the hour.
Hey, Henry, it's
Yes.
the aforementioned Chris. Could you stick
Yes.
around for just a minute to get my presentation started to make sure it's flowing?
Sure, absolutely. But I'm going to stop the recording.
Sure.